The Doppler shift is the stretching or squeezing of waves as a wave source is moving with respect to an observer. The Doppler shift is a general wave phenomenon and can occur in sound waves, water waves, light waves, etc. When a wave source is moving farther away from an observer, the waves are stretched out as shown in the animation on the right. If an observer were to the left of the source, that observer would observe the waves as having longer wavelengths. If there was an observer were to the right of the source, then that observer would observe the waves as having shorter wavelengths. If the source were emitting sound, then the observer on the left would hear a lower-pitched sound and an observer on the right would hear a higher-pitched sound. Though it is a bit hard to see this using this animation, an observer way above, or way below, where the motion of the source is perpendicular to the line of sight of the observer, would observe no detectable change in the wave. In other words, that observer would not detect any Doppler shift. Light coming from sources that are moving toward an observer will have a shorter wavelength. Any features in the spectrum, such as absorption lines, will be shifted toward the blue end of the spectrum. Light coming from sources that are moving away from an observer will have a longer wavelength. Any features in the spectrum will be shifted toward the red end of the spectrum. Again, light from sources moving perpendicular to the line of sight will be unaffected. To illustrate what is meant by perpendicular motion, imagine you are looking at a window in the distance. Any motion that takes place on the window, like an ant walking across it, will be perpendicular to your line of sight. Shown are absorption spectra for objects that are moving away at different speeds. Note that the greater the speed, the more the absorption lines are shifted toward the red end of the spectrum. The line spectra of moving sources can be compared to line spectra of stationary sources that were measured in a lab setting. The amount of shift of absorption or emission lines can be used to calculate the speed of the source toward or away from the observer. Here are power spectra of two stars shown over a very limited range of wavelengths. One spectrum is a lighter shade of blue than the other. On the horizontal axis is the wavelength and on the vertical axis is the relative intensity. Notice that the two absorption lines in the power spectrum of the moving source are shifted to longer wavelengths than those of the source that is at rest. The measured shift, as indicated by delta lambda, would be the difference in the wavelengths of the absorption lines. One has to make sure that the same absorption line is being compared. The absorption line being compared in this example is called the K line of calcium. The shift is found by taking 394.6 nanometers minus 392.6 nanometers. The shift is thus 2.0 nanometers. If the shift is positive, the source is moving away from the observer. If the shift is negative, the source is moving toward the observer. In this case, the shift is positive and the source is moving away. To calculate the radial speed of the source, that is, the speed along your line of sight, this equation is used. The shift in wavelength is divided by the rest wavelength and then multiplied by the speed of light. Whatever speed unit is used for the speed of light will be the unit of the calculated speed of the source. The more detailed equation on the right simply breaks up what was done on the previous slide, which was subtracting the rest wavelength from the moving wavelength. As suggested before, the Doppler shift has a limitation. It only gives you the part of the motion that is heading away or toward the observer. In the top illustration, if the motion of the star is directly toward or away from the observers here on Earth, then the calculated speed will actually be the entire speed of the star. However, if the motion of the star is perpendicular to our line of sight, then no Doppler shift will be observed and the calculated speed would be zero. This situation is depicted in the middle illustration. The star's motion would have to be measured by observing how its angular position changes over time. Then, if we know its distance, the speed can then be calculated. Usually, a star is going to be moving in a random direction with both perpendicular and radial components. The Doppler shift will reveal the radial component of its speed and the angular motion will reveal the perpendicular component. The two components can then be used to find the total speed of the star. Suppose a star is rotating. Light coming from the middle of the star, from our point of view, would be moving perpendicular to our line of sight. We would observe no Doppler shift in the light coming from there. However, light coming from places further and further from the center would have greater and greater radial velocities and would therefore be Doppler shifted more and more. The greatest Doppler shift would come from either side of the star, as shown. Any absorption lines would get smeared out and thus show up as a broader line. This is called Doppler broadening. The faster the star's rotation, the wider the absorption line. Broadening can also be seen in the power spectrum. The spectrum plotted in red is from a star with a faster rotation than the star whose spectrum is shown in blue. The broadening is measured by going halfway down the absorption line and measuring the width. This is called full width at half maximum. The width of the absorption lines in the red spectrum is wider than those in the blue spectrum. The width of the absorption lines is used to determine the rotation rate.